before the midterm, you have learned about what we call the fundamental and the tool part of Bionanotechnology. If you look at your course outline, you will see there are 5 things that we need to cover. So this is your course outline. The first, the second, the third, the fourth, and the 5th. The first one we talk about the fundamental of nano or Bionano, and the second part we talk about tool and meaning that the characterization tool like SRD, SEM, TEM, and so on. And the third part is basically the principle. What is the principle of Bionanotechnology? Principle. The fourth is the technique, and the 5th is the application. Okay, so this is basically your course outline lah. So your final later on will cover everything, even though whatever before the midterm. So you cannot forget whatever you learn, the fundamental and tool. So the final include also the in-class activities, the one that you do, the SRD. Include also the lab visit, whatever you learn during the lab visit, and also include the video that I asked you to watch, the Bionano fundamental, the one that I give the link to. So for the video itself, if you look at the video, in the video that I asked you to watch, you will see that there are what we call, at the beginning of the video, I talk about the what we call definition, right? Definition of Bionano and also nanobio. The definition of Bionano and nanobio. And that is the question that I give you in the bonus quiz just now. So for Bionano, the word Bionano, what is the definition of Bionano? Those who are done the quiz just now, what is the definition of Bionano? Sumayat. What you write on your paper? Sorry?
The use of biological principle with technology at times.
Okay. So basically Bionano, if you look here, the emphasis, the word bio is in front. So meaning that that is the spotlight thing lah. So Bionano basically the use of biological building block, because bio. The use of biological building block, and this, if you want to get the full mark, you need to give also the what we call the what is that thing. So you put in this thing, maybe the DNA or peptide. Peptide is basically the amino acid make like a protein lah, and also its principle. For example, like self-assembly, and also self-recognition or whatever lah. Self-recognition for the development of any technology lah, technology, biotechnology or nano related technology lah, technology. And this technology can be either biological or non-biological. So normally when you give the definition, you give also what we call the example of what is the technology. For example for this, maybe you can say DNA nanowire. So basically normally when you make a wire like that, you use metal, right? So if let's say you want to use a biological building block like DNA or peptide, instead of using metal, now you use DNA as a wire. So you can put in circuit and so on. So whatever application here, it doesn't really matter, because this is just like a proof of concept whether you understand or not what you write. So DNA nanowire is not yet commercialized, but there are people study about that. So they are using DNA as a Lego block to make a wire. Okay, instead of you make a wire from the big block of steel, and then you make it small. Now you have the building block that is already small, and then you make a wire straight away. So that's basically the what we call the example. What is the definition of Bionano? Nanobio, in other words, they what we call give emphasis on nano. So it's basically the use of what we call typically the technique in nanotechnology, the use of nanotechnology technique. For example, like nanofibrillation. Nanofibrillation is basically simply you make things become nano. It's like you have the tree. Let's say you have the tree, and then you want to make a paper, right? In order to make a paper, you use a pulp. Okay, so nanofibrillation is that the pulp is something like this, something like they have fiber like that. That's the pulp. So nanofibrillation is basically you subject this pulp to homogenizer or whatever, high-speed homogenizer or crusher, whatever, so that this fiber inside the pulp will become fibrillated, will become free. Because the pulp itself, if you look here on the paper, if you try to sort of like take this thing, you will see a strand of fiber. That strand of fiber is not yet nano because you can see. So that strand of fiber, let's say that's fiber, the one that you see in the paper, the one that I just take just now, if you look here, if you take this thing, put in the microscope, it's still something like this. Something there are a lot of even smaller fiber. So the word nanofibrillation is basically to sort of like to make this fiber to become free. Okay, because when the fiber become free, you have more surface area. Okay, you have more surface area instead of you have a big blob of this. For example, imagine this 4 marker pen. If I do like this, so you have the contact between each marker pen is quite less lah, because it's big. But if you can make it smaller and smaller, you can sort of like fill in a lot of smaller marker pen in the same area of this lah. So you increase the contact area lah. And when you have increased contact area, you can speed up the reaction and so on. That's already covered in the what we call in the video that I give you lah. The use of nanotechnology technique, nanofibrillation or whatever, or electrospinning. Example lah. Electrospinning. What is electrospinning? It's just basically you have sort of like syringe, pichagari, and then you put a polymer inside. And what you did is that you apply the voltage potential between here and here. Let's say this is negative, this is positive. Okay. Imagine this is this needle is metal lah, because you want to use the electrical current. So because there are potential difference between this and this, when you try to push this syringe, what we call this polymer inside will push forward, and what will happen? They will have like a blob of polymer here, and because there are potential different here, this will sort of like ejected to here. It will sort of like become ejected lah, like from here to here, and along the way, because the distance is as if you want to pull something. When you have sort of like something like a polymer, you try to pull it down, it becomes thinner and thinner. You have a polymer like this, a melt polymer, or if let's say you, just to give you the idea, you know the honey. If you take the honey and then you put like this, you see the honey will drip, and the higher the distance, the longer the distance, the drip become thinner and thinner lah. So that's the principle of electrospinning. They use electric potential difference to force this stretching. We call it stretch lah, to force the stretching, and then by that you get like a strand of fiber that is very thin. From this polymer, like a liquid polymer, you get a fiber. So that is basically one of the nanotechnology technique that you use lah. And also the use of nanotechnology technique what we call to develop biotechnological application lah. Okay, example for this is that example is nanorobot. Example nanorobot for surgeries. Okay, biotechnological or biological lah, or biological. Logical. Because why? Because you have bio here. So whatever you do must relate to the bio in this case lah. So nanorobot here, in order to make something like nanorobot, let's say you use metal, you miniaturize the robot to the size that is you cannot see, and then you ingest it. Let's say you ingest it. Let's say the robot is like this. Somehow robot like this, made from the metal. But because this robot is small, miniaturized, so that's why we call it nano. And then this robot help you to perform the surgery inside your body. So this is biological application lah. So this example lah. So you see the difference between this Bionano and nanobio. In the video, I also mentioned that nowadays people just intermix these two things. This also they call Bionano, this also they call nanobio, whatever like that. That's why in the class I talk about nano because nano. I start with nano because nano is applied for both lah. Anyway, you need to know a little bit the differentiate between these two lah. Okay, so now what we want to do now is that we want to study this part. We want to study the principle lah. We want to study the self-assembly part. Okay. So for this semester, I will focus on the self-assembly part only. So how self-assembly? What is self-assembly? Is that the things self-assembly mean things spontaneously what you call arrange itself lah. Arrange itself. Okay. Normally, for example, let's say you have this marker, you want to make like the line, you need to put this marker here, you need to put another marker here, and then another marker here, another marker here, so you get like a straight line. So this, you need human intervention. You yourself doing this thing. Self-assembly is simply like you throw this marker, suddenly the marker, they assemble itself like the line without you intervene one by one. So that's the idea of self-assembly. Spontaneous here doesn't mean that no intervention at all. Of course, everything happened because of something, right? But what I mean by spontaneous here, I mean that there are no human intervention lah. You don't need to do. Maybe other factors do this thing. For example, like because of the hydrophilic interaction, other thing that doesn't need human to intervene. So that's what I mean spontaneous. It doesn't mean that it just become like that. There must be some force to drive this self-assembly. But that force is not you, it's not human. Okay, so that is self-assembly. So to give the example, of self-assembly, let me have this thing. Okay, where is the paper? So let's say I have the two paper here. I have the two paper, and just normal paper. One paper is nothing. One paper I cut it. So that you get like a bristle lah. I call it bristle lah. So you have something. Let me. What is pemadam? Oh yeah. Okay. So let me rub this first. So imagine now you have something like this, something like this, and then you have like a paper. This is what we call bristle lah. Bristle. Okay. Okay. So imagine you have something like this, and then you have like a beaker. Let's say I have beaker. Let's open je lah. Tak payah ni. Like I have beaker, and then I put a water inside that thing. I put water inside. You can see, right? Even though it's not clear, but hopefully you can see lah. Okay, let's say I put inside here, and then what you think will happen if I dip this thing inside? Okay, let's say I can see you cannot really see very well, but I hope you pretend lah you can see. Okay, so this thing is separate by itself, and then I put inside the water. You can see what will happen. Can you see? No, it doesn't matter. Okay, you can see. And then if I try to pull it out, it will sort of like tak ni dalam sikit, sort of like this is not really big lah, dia kena pecah sikit. So this is too big. Okay, but somehow you will see it's sort of like self-assemble to certain shape. It becomes sort of like contract with each thing. So what is the reason for this? This is basically one of the example of self-assembly. At the beginning, you see the bristle is separate like this. But then once you put in the water and take it out, it becomes like this. So the question now, what force that caused this thing? Why this thing happened? So that is a kind of a question that I might ask in the final or whatever lah. It's more about why rather than what you see. That's observation. But why now? When you take this thing and then you have the water inside, you have the water inside, and then you put the thing inside, and then you take it out. Let's say this thing, you take it out, it will become like that. So become like this. Instead of like that, it becomes something like this. When you take it out lah, this you put inside, like this, and then this taking out. What caused this thing to happen? Any idea? What caused this thing to happen? It's easy to see, but why? The word why is more important than what you see lah. Why this thing happen? Surface tension. How? How do you explain further? Okay. So surface tension, yeah, that's the answer. But how to explain, to elaborate further? Because if you just say, if let's say I ask in a question, what caused this thing? When you explain this thing, discuss this thing, and you write surface tension, you don't get ni lah, full mark lah. You need to explain how the surface tension caused this thing. That's what I want to ni lah, see from you. Okay. So here, when you see this thing happened only when I take it out. Okay. So you cannot say this thing happened because this thing is wet. Because if I put it down, you see, this like this. If I put inside the water, you can see it's expand again. If I take it out, it's only happen when I take it out, not when the water inside. So the answer that it's happened because it's wet is wrong. That's one thing. So you see, because if I put inside, it's still like this. Still like this. Only when I goes up, then it become like that. The reason, like Aiman said, is surface tension, but the explanation for that is what I look for lah. So in order to what we call to create a story of that, we need to understand what is surface tension itself. Okay, surface tension is what you see here is macroscopic effect. You can see with your eyes, but the principle is microscopic. What you see is macroscopic, you can see, but the principle behind this is microscopic or nanoscopic lah. In a water, okay, before I discuss this, let's understand a little bit about surface tension. If you have a beaker like this, and then you put a water inside, you have a water molecule in the bulk. So this is what we call in the bulk. This is what we call on the surface, on the surface. So imagine this is a water. Okay, imagine this is water. So water, there are a lot of water inside the bulk, meaning that there are water molecule here, and so on. So the water molecule, let's say this is one water molecule here. The water molecule inside the bulk, they experience the same pulling force from the surrounding neighbors. So it will experience the sort of like what we call the similar ni lah, net force lah from each direction lah. But so we can say that this thing, the experience similar or whatever, similar pulling force, because you need to remember there are next to this there are another water molecule, next to that ada another molecule. So this water molecule that I draw in red is surrounded by other water molecule lah. So this water molecule experience the similar pulling force in every direction lah, in every direction. But the water molecule on the surface, let's say I draw in what we call in green, only feel the what we call the pulling force by other water molecule downward. So the net, so you can see here, the net force is basically downward, because there are no water molecule on what we call on the top here on the atmospheric. Yes, in the air there are also water, but it's not as strong as this. The volume is limited, because even though the air comprised of water also a little bit, but the volume of the water is less. So it's not enough to pull the thing at this moment lah. But eventually it will pull also lah. That's why evaporation happen. But at this moment, this water molecule on the surface only experience net force downward. So this thing to show that at the surface, the things behave differently at the surface. It's true for the water or liquid. It's also true for any metal lah, because if you see any any material, because in material, solid material, we talk about the surface energy. Okay, there are also concept of surface energy and so on. So the surface tension, normally we use the word surface tension for the liquid lah, for the liquid. So so anything in the universe, they try to minimize their own energy. Anything in the universe, let's say this universe, although this is the Earth, but anything in the universe, they try. Anything in the universe will try to minimize its total energy in the system. Okay, total energy in the system. So this total energy can be sort of like because of the surface tension and so on. When we talk about the surface, the word surface itself give you the hint. For example, you want to minimize the total energy. Let me go for the 2 dimension first. Let's say in 2 dimension, let's say you have a rope. Let's say you have 4 meter rope. 4 meter rope. Okay, what is the shape that give the maximum surface area? Because surface we try to relate. Let's say you have 4 meter rope. What is the shape that give the maximum what we call maximum area? Let's say you can make this rope into triangle, square, circle. Which shape with the same amount of 4 meter rope, okay, is the area here is the same or not? Is the area here is the same or not? Same or not? If you make the rope, the 4 meter rope into triangle, you make 4 meter rope into the rectangle, you make 4 meter rope into the circle. Is the area inside is the same or not? Okay, why? So how you prove it? How you prove that? Let's say we compare this thing, the rectangle and this. For rectangle, not rectangle lah. This is a square lah. Let's say I have 1, 1, 1, 1 because 4 meter, right? So you get the area equal to 1 meter square, right? So for the what we call for this circle, you know the circumference is 2 pi r, right? 2 pi r is the circumference. So 2 pi r equal to 4 meter. So this is circumference. So you want to find the area. In order to find the area, you need to use the area formula. So this is circumference formula. So you need to use this area is basically pi r squared, right? Pi r squared. So you need to know what is r. So because you take here, you can find the r equivalent to 4 over 2 pi. Okay. So and then you put into area formula, you get pi, and then you have 4 over 2 pi squared, and then you get what? 16 pi squared over 16 pi, and then 4 pi squared. You get something like this, and then this you can cancel, you get 16 over 4 pi. Can you calculate this thing? What is the amount of this? 16 over 4 pi. For the rectangle, we see that the area given is 1 meter squared. So we want to prove that for the circle, the area is bigger than that. What is this? 16 over 4 pi? 1.27. So you can see the area is bigger than that by 0.27 meter, using exactly the same length of the rope. So how this relate with the surface tension? Okay. So this, you know this thing. Let's say we take this thing. We take the circle. Okay. Let me take. In 2D, our life is 3-dimensional. This is only 2D. When you are making 3D, let's say you have circle. When you make it 3D, you get spherical, right? You get a spherical. So this, what we call this, the circumference, they become the surface. Become the surface. And the area inside, they become the volume. When you make it 3D, you know, circle, you make 3D. This is what we call the idea of integration lah. You learn about integration, right? You have something like this, y, x, and then you have this. Let's say this is 4. This is y, this is x. Let's say this is so let's say you have this area, and then in order to integrate, you basically integrate and find the volume. This thing, the first time when you look at 2D, it's just like the area, but when you try to find the volume, you rotate this thing, you get something like a cylinder. So the area at the beginning is this area, but when you try to find the volume, the area become the volume. So same like this. So now you have two things. You have the surface, and also you have the volume. Okay, so we learn in the what we call in the video. I also talk about the surface area to the volume ratio, right? So where the surface they increase slower than the volume. Okay, so to relate with this, how this thing relate, the surface and volume. In order to minimize the total energy for a given volume, let's say you have 1 liter of water, you need to put it in the what we call in the spherical container. Let's say you have 1 liter of water. You put in the spherical container and you put it into the cube container. Let's say this 1 liter can be filled exactly inside this container. So you can, the surface area for this is the highest, is the lowest here compared to this. Okay, inside this container there are 1 liter of water. Inside this container is 1 liter of water. If you compare in terms of surface area, which one have the highest surface area, the A or the B? Which one have higher surface area? The volume is the same. The surface area will be different because you learned before, different shape have different area. Okay, but in this case, if you have 1 liter water filled inside this thing, inside the container, which container have the least surface area? This one or this? The same amount of water, but the what you call different shape. Which one? Faham tak? Ada pening. Okay, so it's actually you can calculate for the same amount of volume, the spherical shape give the least surface area. Faham? For the same amount of volume, the spherical shape give the least amount of volume. Remember, don't confuse between 2D and the 3D. So that's why you will see that the raindrop like this, spherical. Okay, because you try to reduce the total energy, because if you have the least surface area, you contain everything the same volume at the smaller area, then you conserve a lot of energy lah. So that's why your raindrop like this. Of course, the raindrop you see something like this, right? So this part is basically happen because of gravity. Gravity, you go down, that's why you have like a draft up, but you see the spherical shape there. So this is the reason how what we call the nature try to sort of like to conserve the energy. So if you look in the raindrop here, if you try to make it bigger like that, and then you see there are also same idea like this. In the middle here, you have the water molecule there, and the water molecule in the bulk, they experience the same what we call same attraction with each other lah, in the any direction. But the molecule in the surface, they try to go inside. Because this shape now is 3 dimension, it's like the sphere, so you can see this thing like that lah, become like that. Like that, it become inside. So this, we call it contract. Water molecule contract lah, contract. I mean, it will goes inside. It goes inside lah. The same thing happen if you have this thing. Let's say I have this thing, and then I put what we call the water inside on top of that. You can feel the thing because it's on the top. You cannot see from the susah lah. Tapi faham kan? Basically, if you put in the what we call in the thing, if you try to fill this container more and more, you will see the water molecule will sort of like something like this. It creates like a skin, like a skin, elastic skin. So you see the water become like this because it's contract. It tries to fill in as much volume that it want before it's break. So that is caused by the surface tension lah. So water, just for this thing, water is a liquid that have highest surface tension lah. Water, the surface tension, you can calculate the what I call the amount of that. How much pull, how much force, because tension is a force, right? So surface tension of the water is around 72 Newton per millimeter squared lah, whatever, something like that lah. So it need the what we call the force more than 72 Newton per millimeter squared like this lah, 1 mm to break the water molecule. So that's why you put water on that beaker, you see this thing is hard for them to burst because they have tension here. Okay, if you put other thing, for example like hexane will not be like this lah. Hexane, if you put hexane or other liquid, it's still like that, but the amount is not as great as it. Maybe like this only, maybe like this, and then they burst. So that's what make this thing lah. So this create like a skin. So this is so strong. I mean, water molecule is one of the highest surface tension among all. Then you can sort of like float the what we call, let's say this petri dish. There are water inside. You can float the paper clip on that. So the paper clip is not like paper clip made of the what we call metal, right? Metal should be denser than the water. But if you put it carefully, then it float. The idea, the key is that you put it carefully, because if you put it in force, then you break lah with your force. So that's why you need to put it carefully on the water ni lah. Then it will float because the surface tension is enough to hold to give the skin for that. Okay, you can break this water tension by putting the soap or surfactant. Soap with detergent or whatever. For example, let's say you have a paper clip on the water like this, and then you put a drop of soap here. The soap, what is soap? Soap is basically surface active agent. I mean the nerd term for the soap is surface active agent lah, but we call it soap lah. So basically the soap have a lower surface energy, a lower surface tension. So when you put the soap, put a drop of soap, you sort of like break, you lower the surface tension of the water from 722, maybe you lower to 40 like that. Okay, so when the surface tension is lower, this thing cannot hold anymore. So it just need less force to break. So that's why this thing goes down. And this also a reason why the water strider. So let's see. Stuff. Hopefully my battery is enough. Okay, you see ayat-ayat on the pond, something like this, something like that. That stuff, that animal, they can move on the pond. So that's based on the effect of the surface tension lah. When you see ship, not biri-biri, a ship, kapal, on the water, even the water shipbed of the metal, the ship can float on the water not because surface tension. That's different thing. That's because of the buoyancy, density, and so on. So you need to differentiate between surface tension. You cannot say that the ship float on the, because this ship, they don't float on top of the thing. You see, they are sort of like den here, right? So the ship, is go a little bit lower than the water. But when you see this thing, if you see from the side, it's exactly on top. Ship, they float because of the buoyancy, density, and so on. We not discuss that lah. But to show you the difference between these two lah. So that's surface tension lah. So back to this part. So how this create this thing? So when you try to sort of like to dip this down, remember this is the bulk, same like this. So that's why you can see even from here macroscopically, you can see the water molecule pull this bristle here and then with the same direction. So there are no preference in direction. That's why you see it just, what we call, it just go just like that. You can see inside, it just go like that. There are no preference of direction. But if you take it out, so there are preference there. They are coalesced. They are sort of like merged together. The reason for that is because if you can take it out, if you see this thing, you will see, let's say I take it one, you will see the water after you take it out, after you take it out here. After you take it out, this one bristle, let's say this one bristle, and then there are another bristle here. The water molecule, they sort of like here, on the surface here. Okay? Because the system try to minimize their own total energy, they combine together lah. That's why they coalesce. I don't know how to pronounce, but that's the thing lah. They try to merge. So that's why this goes here, this goes here. It's not because of hydrophobic or hydrophilic or whatever. Okay? It just they try to minimize the what we call the total energy that is needed lah. So that's why you only see this thing happen, the self-assembly happen because after you pull it up. Okay. So, benda lagi saya nak. Okay, so that's we can say now one of the force that drive self-assembly is surface tension. So we can say self-assembly. One of the force that is drive this self-assembly is surface tension. That's one force lah. There are many other force lah, like hydrophobic and so on, but that's at least one force. So let's see now another force. I need to make sure that the battery, because when my battery is, let me share. Sampai berapa? 8. Hopefully I can do it before this thing lah. Okay. Let's see another thing. Okay, let's say now I put this water with the colouring. Let's say I put with the colouring, with the colouring, with the colouring, food colour, and I colour this thing. Okay, so I just colour this thing, so that's easy to see lah. Okay, so that's I colour the thing, and then I try to take a straw, and then here I have the capillary tube that you used before during the lab 1. Are you online or physical? That's good. So this like a tube. This also like a tube. If I put this open, if I take it and put here, you can see there are some water, but it's not so much. Okay. But if I take, pegang, penat lah saya nak pegang banyak benda. Okay. If I take this, if I put inside, take it out, nothing happen. Why? Because this is closed. Okay. I need to open it to make it happen. Open this thing. If I put here, you can see the water until nampak. Nampak tinggi tak? Tinggi tu. Whatever lah, padahal lah you. You tengok sendiri, you pass around lah. You pass. Tak apa. Benda ni boleh beli. It's okay. So you can pass around lah. So you can see that what we call the water goes sort of like higher compared to that. And let me show. Biar dia. Nah, good. Okay, so as you can see just now, because I'm more worried about this than that, because this, when the battery is below that the specific level, then it's hang. Anyway, it's okay. So you see just now, I put the straw inside the water, right? So you can see, I need to cut. And if let's say they are sort of like they are close here, and you have water there, the water will not rise up. Because why? There are no pressure. Because imagine in the air here there are pressure. So the pressure push this water. But because this is closed, then it cannot go up lah. But if I open this thing, let's say I open this thing, I open like this, and then that thing, and then you have another one. So basically there are still pressure, but now you have this thing. Because when you open this thing, this is the low pressure part. So the water will be pushed inside, and then the water will rise lah. So you need to open the make it boost open lah in order to that to happen. But this I don't want to talk about this. I want to talk why this water goes up. This water goes up at the first place. Okay, why the water goes up at the first place? This water goes up because of what we call capillary action. Okay, so this happened because of capillary action. Okay, if you look just now, if I use the big diameter of something big like this, and then the same thing I put in the beaker like that, you will see the water just rise very at this not too high lah. But if you use a capillary tube which have a lower smaller diameter, then the thing goes rise very high. And the reason why I can do this thing when I can celup and I take it out and it's attached here, because inside this popsicle, there are also what capillary lah action happen. That's why it's absorbed inside. Because imagine the tree, how the tree, you have a tree, and then you have the akar roots, and then how the water, you water here, right? You water or nutrient also here. So it goes up through the capillary action like this lah. So because inside the tree there are like small tubule of xylem, they call it xylem or whatever the name. So that's why it can raise up. But the question what we want to answer here is that why this thing happen? And this happened because of the meniscus. Okay, and this meniscus, or what we call the capillary action, can drive the what we call the self assembly. But before we talk how the meniscus drive the assembly, we need to discuss first what is meniscus. Before we talk about how this thing, how whatever you see just now, can drive self-assembly, can make things arranged by itself, we need to understand first what is meniscus at the first place. So the second is meniscus. Meniscus. Okay, meniscus will cause capillary action lah. Okay, so that is a driving force. But before we discuss how it drive, we need to talk about meniscus by itself. Okay, let me close this thing. Close pula, erase this thing. Okay. Meniscus. Okay, the meniscus. The word meniscus, what does it mean by meniscus? Yeah, before that I show you something lah. Okay, this is okay. It's okay, this is okay. You can see right? You can see right? Okay, let's say I put here. Sekarang pukul apa? Kita habis pukul apa? Okay. Let's say I have this bowl and then I have this water. You can see right? There. I put water and then I put just a small amount of apa ni? Ni apa? Sabun. Just small amount. Small amount of sabun. And then I try to kacau-kacau. Sah. Okay, you can see the bubble there. You can see. Mana sini? You can see the bubble, right? So I put in the middle. Okay, but you can see over time it goes to the side. It goes to the side. It goes to the side. Okay. So normally when you have a soup or whatever, you order the soup in the shop or whatever, you see the bubble. Over time the bubble will go to the side rather than stay in the middle. So why that happened is because if you look in this what we call because if you look just now, I inject the air inside here, right? Inside. This is the bubble. The air is inside. So the air bubble is less dense than the water lah, liquid water, than the water. So because it's less dense, it will goes up. It will goes up lah. Eventually it will goes up and it reach to the surface. Okay. Eventually it will reach to the surface. Once in the surface, if you look here, all the bubble go to the side. The reason because if that on the surface here you have this what we call the gradient there. Okay, so the bubble here goes in the surface. It feel the upward force, still feel the upward force. It's not stop there. It goes to the side there. So that's why all the bubbles goes to here. But the question now, why this thing happen? This is what we call meniscus lah. Let's say this is the surface of whatever. The question now, why this thing happened at the first place? Why the meniscus happened at the first place? This is caused by the cohesive and adhesive. This is because of the cohesive and adhesive force. Adhesive force. Okay. What is cohesive and adhesive? Cohesive is basically the attraction force between the same molecule. This is basically attractive force. Attractive force between similar molecule. And the adhesive force is basically the attractive force among or between lah, between non-similar molecule. Okay, if you look there in the bulb, in the ball. This is glass, right? This is water. So you have water molecule, you have glass molecule. Cohesive force meaning that, let's say like this. So the water and water. You have the water, H2O, and also you have the water. So they sort of like cohesive lah. They sort of like attract with themselves, with their own their own species, like that. Adhesive force is happen when this attraction happen between dissimilar object. For example, water and glass. This is water molecule, this is glass molecule, two different things. So that's we call adhesive force. So when cohesive force is bigger than the adhesive force, what will happen? For example, adhesive is dissimilar, right? This is what you call? This is similar molecule. This is dissimilar molecule. So what will happen? Let's say I have this surface. Let's say whatever surface, and I put the water drop on that this. So if the cohesive force is higher than adhesive, let's say cohesive force for the water is water is higher than adhesive force between water and the surface. What you see will happen when I drop the water here? You will see the water will beat up, because the water like themselves more than they love the surface. Okay, the cohesive force between the water molecule among themselves is higher than this water with this surface. So now, if let's say the adhesive force is higher than the cohesive, so what will happen when you drop a water on that surface? Let's say this is the surface and that color lain lah. They will collapse. We call it collapse. The water collapse. The water collapse macam ni. So dia lebih suka surface. This is what we call wetting lah. Wetting. We call another word wetting. The water wet the surface. So this happen when you see a certain thing, it beat water daun keladi. Daun keladi dalam bahasa Melayu apa? Dalam bahasa Inggeris apa? Daun keladi. What is daun keladi? You know daun keladi? Yelah, Al-Sumayyad and Ubadah and Hashim. Daun keladi dalam bahasa Inggeris, tapi daun keladi lah. Daun keladi air. You see this thing? So that is daun keladi for Hashim and Ubadah and Sumayyad. We call it daun keladi. So you see when you have the name for this? What you call this? Oh, you never see this thing? Have you ever seen this leaf? Have you ever seen in your life this leaf? What you call that thing? Lotus. Lotus. I call it lotus lah, lotus. So you can see the water here. The water cannot wet the lotus leaf. Bunga teratai, even though it's not bunga teratai. Okay, that is lotus. So that is basically what happened here is that the cohesive force between water molecule among themselves is higher than the adhesive force between water molecule and the lotus leaf. So that's the idea. So when you have something like this glass, when you have the tubule like this, let's say you have the glass like this, and then let's say you have the thing. Okay, then you put the tube inside the water. What will happen is that the water has here, we can say that the adhesive force is higher than the cohesive. The adhesive force between water and the glass is higher than the cohesive force between water and water. That's why you get like this. So if you have water, you get the meniscus like this. But if this is water, right? Water in let's say in capillary lah. Capillary. But if let's say you have another liquid, for example, the mercury. This is mercury in thermometer. You see this is concave up. Concave up, this is concave down, right? This is concave down. Concave down. So, this concave up, it shows like this is because the cohesive force of mercury between mercury molecule is stronger than the adhesive force between mercury molecule and the glass. Understand? Okay. Okay. So that's why when you do something on the glass bowl or whatever, you get something like meniscus. We call this meniscus lah. So when you dip a tube in the water, whatever, the first thing what happen is that this thing will rise lah, because the glass and the water, the adhesive force for the normal glass with water is higher than the cohesive force. That's why they ni lah. So this also become like this, and then this also they become like this lah. It become like this lah. It become like this. Now inside this, so now this is the first thing what happened. So the water will start to wet. The first thing, the water start to wet the glass. So you get the meniscus like this. Okay, the second thing that happened is that, so you get something like this lah. Something like this lah, more or less like this. The second thing that happened is that, because we learned about the surface tension before, the system try to minimize their own energy. So you will see in here, they will try to contract. Instead of become curvy like this, it become not less curvy lah, less curvy. Because this is not much, because there are no boundaries, so it's not really much. Because here they are not as curved like this, because there are no boundary. So they still like they are curved, but it's not as pronounced as inside, because the inside here there are boundary between the what we call that contain the water. So that's why you get a more pronounced curve. But because of what we call the system try to minimize their own energy, what will happen when we learned before, the water molecule contract. So instead of like this, it try to contract lah, Because if you compare this and this, it's not the same lah. This have less surface area lah, less surface area than this. Because this is like they go down like this, and compare this and this. This is have less surface area lah. This is more surface area. More surface area. So the system try to minimize. That's why they try to contract. So when they contract, when the water molecule surface contract, this curvature contract, it will sort of like bring the water up lah. Because it's contract, it will bring the water up. So that's why you will see the water will goes up lah, until to the point the surface tension is in equilibrium with the weight of the water itself. Because in the capillary, you will see the water rise up until certain point only. Because what happened there is that the equilibrium is reached between the surface tension and the weight of the water itself. Okay, so the smaller the what we call the tube, the more pronounced this contraction. Hence, the more water can be raised. Okay, that's why you will see in the what we call in the straw, it's just a little bit only, but in the capillary tube, it goes a little bit higher. Okay, so that's the idea for that lah.